can check, I believe that's the problem you're talking about. Right? And what method did they ask us to use here?
Superposition.
All right, you know, it's done by superposition, so we have to basically solve a circuits problem twice. Do you agree with me? I'm going to call this source 1, and I'm going to call this source 2. All right? So now I'm going to turn on source 1, turn off source 2. Because I'm turning off the 6 milliamps, what is that? What do I replace it with, class?
Open.
Open circuit. You just erase it, right? It's not there anymore. There's no current to flow. So when I do that, this is going to be the first part of this problem. Now I have 12 volts. Then I have, you'll notice that's not there, so I simply have 12K, and I have 6K. 6K. And then I have 12K, and I have 6K. And I want this current, I0. Y'all agree with me here, class? Who asked this again? All right, y'all, you see what I'm doing, right?
Yes, sir.
Now, by this time, most of you pick up on this fairly quickly. These two are in series, do you agree? That's a total of 18 K ohms. These two are in series, that's 18 K ohms, right? They're both across 12 volts. The current through this one, therefore, that current I0 will be 12 volts divided by the series resistance of 18 K ohms, or it's 12 over 18, right? Or it's what? 2/3 of a milliamp. You could put 0.666 milliamps. Do you agree with me, class? Show of hands here, how many see that? It's that straightforward, that's the first part. Now the second part says we turn off the first part, right? Correct? We turn off the voltage source. So we're turning this one on. What do we do with this voltage source, class?
Short circuit.
Short circuit. Now I'm going to do it here if you don't mind. Are you with me? So if I short circuit, it does this. You agree with me? Now I want you to notice something. Here, it's a little bit different because I need to do a redraw to appreciate this problem. Let me just show you this one, the way I do this. And I know you're new to this, but if you do any kind of fluid work, or you do hydraulics, or incompressible fluid dynamics, or you have any of these courses in aerospace and in mechanical that deal with fluids flowing, either compressible or incompressible, and multiple ways for things to flow. You know, you have to figure out what has the same pressure, what has the same amount of fluid through it, or series parallel, right? The way I do this, I'm going to put the 6 milliamp vertical here so you'll see this easier. This is the 6 milliamp. I'm going to do a redraw. Now, I'm going to start, and I'm going to start off the way the current's flowing out of there, and I'm going to use a colored marker, blue, and stop whenever I hit a resistance, all right? I'm going to take a different colored marker. I like this because you can't mess this one up. And I'm going to say everything I hit there, right, between, I come off and hit, now I start drawing off the tip of that. I've hit a 12, this one, and I hit a 6K. So I got 12, 12K, and I hit a 6K, right? You see what I'm up to, class? The redraw is the one that gets people in this one. Now I take a different colored marker, green in this case, and I go to the other side of the 12K, and I come here, and I go through all the wires, and I touch everything, and everything between the green and the blue is in parallel. Can you all see that? Green and blue. Now, I want you to look at this for a moment, if I can. Show you, some of you appreciate this, that I basically have this 6 and that 12 are in parallel, right? They're between the green and the blue. Do you agree with me? All right. Now those two are in parallel, and that's really where it stops, right? Because I've got this part too. So now I need another color marker, and I'll go on the other side of this 12. By the way, I'm going to draw this. When I come through there into the green, I have two resistors that I hit. I hit the 6K and 12K over here. And so I hit a 6K, and I hit a 12K here. And now I take another colored marker and I come here, and I go to the other side of 12, and then I'm back to the actual start. Now, anything between the red and the green are in parallel too. So if I look there, I have the 6 and the 12 in parallel. Yeah. And then they go back to the actual source. Do y'all see what I've done there so far? Can you see this, class? Now, what do I want though? I want the current right here, right? That's this current. I want that current, don't I? I'm going to see this right here. Some of you are very good at this. The mechanicals are great at this. They can almost do it in their mind. They can see how they can bend these two wires around and take this one, literally take this whole thing and flop it this way and then combine them. They can see that really quick in their mind. Some people can do this. Like some people are really good at chess. They can see things. Others have to do that, at least for a while. But you all in time get to see what's in parallel and what's in series. I use the colored markers. To me, it's easier. Y'all see what I'm doing here? Now, follow me. How much current flows down this 6K? Now think about this. Doesn't all the 6 milliamps flow through both of these two resistors? How many see that, class? Y'all see it has to, right? It's flowing there, some flows there, some flows there, but it all has to come together and flow that way, right? That's 6 milliamps going there, there's 6 milliamps. So couldn't I use simple current division to get that value of I naught, class? Do y'all agree with me? So if I want I naught here, I could use current division. Current division says my I naught will be the total current, 6 milliamps, right? Then it's times the opposite resistance, 12K, over 12K plus 6K or 18K. Well, that means the total current flowing there is going to be what? It's going to be 2/3 of 6 milliamps, right? So that's going to be, look at that, that's 4 milliamps. Do you agree with me? Everybody? That means the total current, this superposition of this plus this, I total would be equal to 2/3 of a milliamp plus 4 milliamps. And is that the answer? It is posted. Okay? There might be 4.666 milliamps or some formula. Is that it? All right, you all see what I've done there? It's just analysis. The hard part of this one is this redraw right here. All right, follow me, it's the redraw. Work on that and you'll see it. And the colored markers, trust me, help. They help a great deal. Everything between the colors, I mean between the blue and the green, and between the green and the red are in parallel. All right? You start, the blue starts off the 6 milliamps, the red returns to 6 milliamps. You go through it and see. I hope this answers your question. Other questions? That's a good one. Other questions? Now I gave you source transform problems, and I gave you a bunch of them actually. You had no problems with those? At all? Did you? Did somebody ask me a question? I can't understand. Yeah.
I'm sorry, what did you get for the current in the second part of that superposition problem again? I didn't. Okay, cool. I did it a different way.
Well, you did it a different way?
I had the set up, which I guess mechanically equivalent.
Well, you can have, I'm going to tell you one thing. You can flip this circuit any which way you want, you know? You can, it doesn't matter the orientation of things. You can put the current source instead of vertical horizontal. So it can look a lot different, but it has to electrically be the same.
Yeah.
All right. Yes?
This might be a kind of a basic question, but when you do the redraw, is that just part of these steps to figure out the problem, or is there a key identifier?
Well, yeah, the redraw, in my opinion, is important to do, because you could solve each one of those circuits with nodal, or each one with mesh. But usually if you do a redraw, you don't need either. It's super simple. It's either current or voltage division usually. That's the reason I do a redraw, to make it easier to see. But yeah, you could use nodal or mesh for that. Yeah.
Can you work 271?
7-1?
Yeah.
Yeah. All right, they say source transforms. I want to tell you, these problems, you can use either mesh or nodal or source transforms to solve any of them. And I'm going to show you one more technique today that'll be the final one, and that's using a Thevenin-Norton equivalent. You can solve any of these problems using any of those methods. However, for this one, it says they wanted to do it with source transforms. Follow me? Now, it's important you see these finer things. You see that this is a resistance in series with the voltage right here. You all see that? Now, the whole idea of source transforms, it says if I have a resistance and a voltage, and I have two terminals, doesn't matter the orientation, that is A and that is B, that is identical and equivalent to another circuit where you have a current I equal to V over R, and now the resistance is in parallel, and R, and that's A and B. You'll notice the polarity of the voltage source is, the positive is leaning, or is closest to A, it goes to one single resistance, right? Negative is closest to B. In this case, positive current flowing out and away goes to A. The negative, or from the negative term will go to B, or the current would be coming from B. Try to make sure you get this orientation right. Plus to minus arrow up on this side. Follow me, class? Got to make sure you get that. Now, or if it was arrow plus on the bottom, then the arrow here would be going that way. All right, make sure that. For this one, these two are the key. You all see that I basically have A and B right here. Can you see that? That one has got the wire bent. It takes this and bends it right here. We just straighten it. Follow me, everyone? Can you see it? So what I can do is put a current going into that like this, and put the resistor in parallel. I'm going to do it right here to make my life easier. So, but you'll notice the current is going down. Can you all see that? Because the positive is up towards the bottom. You have plus and then minus. Can you everybody see it in the back there? All right, so I'm going to have a current of 12 over 6, or 2 milliamps down, in parallel with 610. That's the first thing I'm going to do. So now I have a current going this way of 2 milliamps and a resistor here of 6K. Can you appreciate what I'm doing? This is a good problem. I'm glad you brought that to my attention. Are you with me, everyone? It's a little different. The thing's not bent like that, right? And it's right in the middle of the, you might say, the circuitry, rather than at one end. You follow me in this class? Now, what do I do with these two current sources? I got 2 milliamps going into this. I got 4 milliamps going into that. Both, what? Starting at the other side, they're in parallel. Do you agree? What do we replace them with?
6.
Just add them up and replace them. Yeah, that's right. Get rid of one, make this 6 milliamps. Add them up. That's it.
Do you agree with me? Now with source transforms, you go from a series resistance, series voltage, to a parallel resistance, parallel current source, and then back, and vice versa, back and forth. So now I take this here, and I make it a voltage source in series with 6K. You see how I'm absorbing one element. I'm reducing the number of elements in the circuit by one every time I do a source transform. I absorb elements. You see this, everyone? I'm combining things. So for this one, I'm going to get a voltage with a positive polarity downward of 6 milliamps times 6K, or 36 volts, right? And it's going to be in series with 6K. Can everybody see that and understand what I'm doing? Give me a show of hands if you do. I want to make sure that nobody's puzzled. So now, I go ahead and I get rid of this. I'm going to put my 6K right here. And now, I have plus to minus 36 volts here. Follow me? I just did a source transform with the current and the resistance. Now you by this time see what I'm up to, and most of you are very smart. I combine these two and I get 9. You agree? I'm speaking the truth. Engineers draw the smartest of the bunch. I know pre-meds will argue they're better. Pre-meds want more money, but engineers, I have plenty of engineers go to med school and decide, I want to make more money, I'll go be a medical doctor. I'm telling you, this is the field that is, in my opinion, the most challenging. Now, I'll probably get a call from the dean of COSAM, ranting about how dare I do that. Oh. That's 9K. You agree with me? Now here's one thing I want to underscore. The last thing you do is put the resistor or element that you want the voltage or current through in. You never source transform. So I'm not going to source transform this. Got me? But I want you to notice something that I'm going to notice said explicitly. If I have plus to minus 4 volts and I have plus to minus 10 volts, do you see that that is equivalent to a single voltage source of 14 volts? Do you all see that right there? You can add voltage sources together if they're in series. Just combine them. Follow me? And if I put a battery, or I'm sorry, if I put a resistor here, R, the only thing you would need to do is put a resistor here, R. It doesn't matter where the resistance is, as long as it's in series with the two. Agreed, class? Now keep watching. Here, I have, from this point, I have a decrease of 12 volts, right? And then a decrease of 36 volts. Do you all see that? Or really a decrease of 48 volts. Do you agree? From here to here, which means I can get rid of this 12, right? And just make this minus, or put 48 volts here. How many see that right there? Now, at that point, how many see you could use voltage division to get V naught? Just to raise a hand. How many see if I wanted the current here? Now it would be flowing this way, by the way. Positive current would be flowing that way, because that's the positive terminal. If I wanted that current, I could just take 48 divided by what? 12K, right? That would be 48 volts divided by 12K ohms. Or really, it's going to be 4 milliamps. You look at that. You agree with me, class? And then if I wanted this voltage, well, this voltage would, the way it's, the polarity is plus to minus. The actual voltage will be set up plus to minus, and it'll be 4 milliamps, 3K, or 12 volts, which means this voltage will be minus 12 volts. How many see this right here? Guys, you all see it? Who asked that? Does that answer your question?
Yes.
That really the addition of current sources is key, and also being able to start with the one that you can actually start simplifying from. In other words, dead center in the middle. I can take that and make it a current source and take the 2 parallel current sources and combine it. Yeah?
Why is it minus 12?
Well, you see how this is 48, this is plus to minus, right? Current is driven this way, right?
Okay.
That means positive current enters a positive terminal. It's plus to minus. So the actual measured voltage is like turning the leads in your meter around. And if you've ever done this, measured a car battery wrong, you get a minus 12, right? That's basically what they're doing. They're getting a minus 12. That's it.
Other questions about that? Going once. Don't be, I mean, if you got a question, ask it. There are no dumb questions except usually the one not asked, or the one about, well, do I get out early tomorrow? Something not pertinent to the lecture. All right, now we're going to be talking about the last of the techniques we use for analysis. And this is really important one, and it's used all the time, and it simplifies your life greatly for complicated circuits. It's called the Thevenin or Norton equivalence. And I'm going to start with Thevenin, which is voltage. So with Thevenin equivalence circuit analysis, it does this. You can have a circuit made up of a ton of resistors, a ton of sources, a ton current sources, etc. All that stuff. But you only care about the actual, what you want to do is this. You want to take all this stuff on a circuit. Maybe I should draw it this way so you'd be a little more clear about what I'm trying to get at. Suppose you have a voltage source here, V0, got a resistor here, R1, another resistor here, R2, another resistor here, R3, voltage source, or now make this a current source, I here, another resistor here, say we put a voltage or current source here. I want to make this as complicated as I care to, call this I1, I2. And then I have a resistor here, and you want to know the voltage on the output. All right, so I want to know this. I'm going to show you a way to do this and make life easy. Yes? I can't hear you. Thevin, Thev, or Thev. E-N-I-N, I think I spelled it wrong. E-N-I-N. It's in, I don't know if it's in your book actually. It's extremely powerful, just Google it, all right? It's used by everybody. When I come out here, this is the steps. Please write these down. Write them down. The first thing is identify or locate load. And the load is the resistor R that you care about I or V through. What you do is locate the load. The load is always the resistance or the element you want information about. You want either the current or voltage through it. Follow me? Once you locate the load, then in this case it's R5. So R load is R5. Then second is remove it. Remove it. So now I remove it. And now I have a voltage here. I have some unknown voltage, right? So this is going to be V out. I'm going to show you how to do this. Or I'll call it V Thevenin. Call it VTH. Now, this is important. We're going to use this voltage to get the circuit. After you remove that, the third thing is you find VTH. You find the open circuit voltage. This is the open circuit voltage across the resistor that you care about information on, all right? How do we find that? In this case, to find this one, well, no current flows this way. Do you all agree with that? It's an open circuit. No current can flow, right? You all see what I'm saying? If there's nothing here, no current can flow that way. Do you agree with me? That means the voltage here is across this is the same as the voltage across this. And I'm not going to get this for this circuit, but we could get this voltage pretty straightforward because we've got I going there, I going there. That means this voltage here is R3 times I2 plus I1, right? And then comes here, then you get current division here and here. Well, actually, it'd be a little more complicated doing this part, but you could do a source transform there. Anyway, when I do a real problem, I'll go through it, but you could easily get in most problems VTH
VTH, the open circuit voltage. Got me? I think in the book he also calls this V open circuit. So this might be V open circuit. They're the same. It's the open circuit voltage, right? Then, this is the important part, pay attention. Then what you do is you turn off sources, all current and voltage sources. That means voltage sources become 0 ohms or short circuits, and current sources become infinite ohms or open circuits. Open circuit. So once you find VTH, then what I do is take all the current sources out, and I short all the voltage sources, so like this. And then the fifth thing is find RTH, or really the resistance between these two terminals. Do you follow me in this class? Now for this one, I did this on purpose to make it a little more complicated than it need be. If I look at the resistance, this would be in series with this, right? So R3 plus R4, and these two would be in parallel, plus the parallel combination of R2 and R1, right? That would be the net resistance. Now, once you do that, once you find this RTH, you build this circuit. You put V open circuit here. Then you put R Thevenin here, the Thevenin resistance you just found. And then you reattach your load. Then you put plus to minus, now you put your load, RL, back in, and you find either the voltage or the current through that. Follow me? Yes, sir.
What is that on the far right after I goes to infinity ohms?
It's open circuit, OC, open circuit. Okay? Now the way I'm going to get this through to you is do problems. That's where you'll see this. And I'm going to hopefully get 3 into it today. All right, now this is, what I'm doing here, this is a very, very powerful technique, and here's why. Because a lot of times, you might have 10 different loads that you're going to attach to the output of some circuit. Well, if you want to, you can analyze the circuit with all the elements with that load. But if it's a linear circuit, then you have only 2 elements here, and when you can start changing the resistance value, very quickly see what happens. You follow me? And you don't have to do that large-scale analysis every time. Are you with me on this class? And this works really well. Matter of fact, it's the quickest way to get a single value. If you want I naught or V naught in all the circuitries if you do this, you'll see it's super fast. And I'll prove it to you, or at least I'll show you some examples. But now I'm going to apply this to problems. And you can do any of the past problems with this technique. So, we're going to do 273 with Thevens. We're going to do a bunch of problems. You can do them all with Thevens. So it has this. Two K ohms. 3 K ohms. That's 2 milliamps going down. Two K. 2K. What does he want? Oh, he wants this current. He's after this current, right? So I'm going to apply this thing according to the rules I put up. The first thing you do is Can you take a look and see if it is? I mean, let the kids see next. Okay, it is. All right. Now, if you take a look, the first thing you do is identify the load. Look at it. What is the load? What is the thing that we want information about? Pardon me?
Yeah, it's this resistance, right? So it says identify, good. We found that our load is equal to 3K. It's 3K. Now, remove it. Since they want current entering that, I'm going to just label that the plus and this the minus. Are you with me, class? I've identified it and I removed it, right? Everybody with me? Next thing I want is going to be the voltage between here and here. I want my V open circuit, plus to minus. Well, I want you to watch this. This is really simple, but you got to watch it the first time. Everybody with me? Now, y'all see the current can only flow this way in this circuit right here, sub-circuit. Do y'all agree with that, class? Hey, Suman, there's no quiz today. You know, I'm sorry. Tell him what's his name, but he doesn't have to come in. All right. So the current's flowing this way. Are you with me? So this is going to be plus to minus 6 milliamps times 2K or 12 volts. Do you agree with me? All right. Now, what about here? What do you see happening? Can any of this current flow this way, class? Why not? You're right. Why not? It can't flow back. This is an open circuit. That's like an infinite number of ohms. You all see this? There's no way current can flow around if the wire's been cut. You got me on that, class? Since the wire's been cut, all the current has to flow this way, right? You all see it's all flowing this way? People? How many see that? If it's all flowing that way, can't we put these two in series? I'm going to do that too. So I'm going to go ahead and just make this 4K, right? Now, for the record, what is the voltage across that 4K with polarity? I got 2 milliamps flowing through 4K is 8 volts, right? 8 volts. And positive current enters the positive terminal. So the polarity would be plus to minus 8 volts. Do you all agree with me? I'm going to show you something else to get this open circuit. Be attentive here now. Force yourself to be attentive. This is important. Now, when I want what V open circuit is, what I do is I start at the negative terminal. Remember, you can't sum voltages through a current source. Remember that always. You come here and I come this way. Is this a voltage increase or decrease from this point to this point? Increase of 8 volts. I keep going around, right? How about from this point to this point? Increase of 12. Total is increase of 20 volts. So I've got V open circuit. Everybody with me on that? See what I'm doing? Give me a show of hands if you do. Now, next, this is important. The next thing I do is I turn off the sources, right? This is RL. Now we got V open circuit or V Thevenin equal to 20 volts. Now we have to get R Thevenin. And the way to do it is turn off the sources. What do we do when we turn off a current source? Erase it, turn it off, it's an open circuit, right? Just disintegrates. What about this one? Same deal, right? Get rid of it. You all agree with me? Right? Turn off the, if there are voltage sources, they become wires, short circuits, right? Now, here, what is the resistance between these two? You can forget that 8 volts now on that one. Well, just start at one terminal. You all see these two are in series? It's just 4 and 2, isn't it, K? Or 6K. How many see that? It's 6K. You all see this, class? 6K, got it? It's 6K ohms. Right? They're in series. Everybody. Now build the circuit. So what does the circuit look like? You put the open circuit voltage here, which is 20 volts. Then you put the Thevenin resistance in series with it. 6K. Now, that's your plus, that's your minus terminal. I've just built the Thevenin equivalent circuit to everything, and now I apply the load back in. And what is the load? Well, the load was 3K. And now did he want the current? He wanted the current. So what would the current be through that 3K by inspection? It would be 20 divided by 9K. Do you agree with me, class? Show of hands. You see it? So it'd be 20 over 9K ohms, and whatever that is. Huh? And that's really it. It's a little over 2 milliamps, just a shade over 2 milliamps. Agreed? Yes.
When you wrote the 12 volts next to that 2K ohm resistor, that was just the 6 milliamp current source.
It was the current causing it, right? It was just circulating current. Yes.
When you remove the resistance, load resistance.
That was, yeah, because we wanted the current to that, so that's the element we take out.
Right, and you created V open and there was an open circuit between the two. You had 6 milliamps on one side of the open circuit and 2 milliamps on the other.
But it couldn't flow through that open circuit, could it? So the 6 milliamps was confined to flow through the resistance parallel to it. And the other current was confined to flow through this, there was two 2K resistors in series with that, do you remember?
Yeah.
All right, so by pulling that load out, it prevented any current from circulating around from the tube, or really from the, 2 milliamp source through to the other side, if that makes sense. Y'all understand what I'm saying there?
Okay, I see now.
All right.
I was thinking that the bottom wire was connected to.
It is, but there's no way current getting on there can get back, so it doesn't go there.
Okay.
You gotta have a closed loop. That's a good problem. We're gonna do a couple of them. Now that's one of them. Let's do 2.49 we're gonna do problem 2.49 using this technique. I don't even know what that one is, but yeah, it's a good one. No, wait a second, let's do the more I think, let's do 2.75, it's a little more complicated, and I've only got about 10 minutes left. All right, they want us to use Thevenin's theorem to do this. I'll show you Norris too. It's literally a sister to this. It's almost the same. So for this one, that's the problem. They want us to find this voltage, right? So let's go through the steps. First, identify the load. What is the load? 4K. RL equals 4K. Second is remove it, right? That's all in one step, so I'm going to remove it. Now I want to find my voltage right here, right? Please watch this. So I want to find V open circuit or V Thevenin. Now to do that, what do you see happen? I want you to just see how simple this becomes. How much current can flow this way? Just tell me. 0, right? Why not? Because it's an open circuit. Nothing can flow around there. Follow me? All right, there's 2 milliamps. Which way must it flow? Are you with me? Therefore, what's the voltage across this 2K? 2 milliamps times 2K is 4 volts. Do you agree with me? 4 volts. Now, look. What's the voltage across this resistor? First, what's the current through that resistor? What's the voltage? 0. 0 current times R is still 0, right? There's no voltage across that 2K. Got that, everyone? Now, we start at the negative terminal to get the open circuit.
go around. I can't go this way, that's a current source, right? You can't add a voltage through a current source, so I go here. The voltage from here to here is a increase of 12 volts. Do you agree with me? I keep going, I get a increase of 4 here added to 12, or now I'm at plus 16. Do you agree with me? I keep going, now I got 0, so I got 16 volts here. Does everybody see that? I'm adding the voltages in series, right? Starting at the negative terminal here. I see this is increase of 12, this is increase of 4, that's a total of 16. Nothing there, so it's 16 volts. How many see this? All right, are you with me? Can you guys see it back there okay? All right, guys, get their eyes. All right. Now, so I got V open circuit, or V Thevenin, equal to 16 volts. Now, the third thing I need is to find R Thevenin, or the resistance between these terminals. And what did I say you do here? You turn off sources. So V goes to 0 or short. I sources go to infinite ohms, right? Or open circuits. Correct, class? Yes. I'm sorry.
When you got the voltage, why did you go from the negative terminal to the positive terminal?
Well, the way you always get voltages, we could write an equation for the loop voltage. We could start, here's the increase of 12, increase of 4, 0, and then decrease of VOC. But just take VOC to the other side and make it positive. Okay. All right, that's the reason. Okay.
Can you explain why it's an increase of 4 volts instead of a decrease?
Well, if you go from here to here, you all see, whatever the voltage is here, call it 0 volts. This is going to be 12 volts greater, right? So it's an increase. That's it. All right, now we want to go ahead and do the part where we calculate R Thevenin. What did I say we do with voltage sources, class? Short circuits are wires, yeah. Wires are good. What do we do with the current sources? Just erase them. They're a nuisance. All right, with me? Now take a look at that. I want the resistance between the plus and minus. What is it? 4K. How many see that? Just add them up there in series, right? 4K. Now redraw the circuit. Right? When we redraw the circuit, we take this voltage. I can put it any way I want. I can make a battery. I can make just a little circle. Put 16 volts here. Put the resistance or Thevenin 4K. Then I put my terminals plus to minus, and I don't have to put plus and minus, but I do anyway. And then I put in my load, which is 4K as well. And they wanted this voltage right here. What's that voltage going to be just by looking at it? 8. Matter of fact, you got two resistors in series, they have to have the same voltage across it. By definition, they have the same current. 16 is total. 8 and 8. You can do voltage division and get that too, right? So this is going to be simply 8 volts. Agreed. How many see that? What's the current flowing through that? It's going to be simply 8 over 4K or 2 milliamps, right? That's it in a nutshell. Now I'm going to show you one last thing before we get out of here. This is called Thevenin analysis. By the way, Thevenin and Norton are very famous engineers. Norton was at Bell Labs, I believe, and I don't know where Thevenin, probably in France, but I'm not sure. Anyway, these two techniques are almost identical with one difference. With the technique called Norton's analysis, use Thevenin's if you're ever given a shot, but I'm going to show you what Norton's is. For Norton's analysis, we do this step, but the difference is the very next step. We first identify the load and we remove it. Then, what happens is this. Instead of, well, you could say second thing is find R Thevenin. Then you find R Thevenin just the way we've done in the past, all right? We turn off the sources, got me? But here's the thing that's a little bit different. The third thing is, now we find I short circuit. Which means we replace our load with a short circuit. All right? And instead of finding the open circuit voltage, we find the short circuit current. Now this is just I short circuit, and I'm going to do a problem. Do y'all understand me? This is the difference. Then our circuit looks like this. we put I short circuit there, and we put the resistance R Thevenin in parallel, and then we put our load on. Then you go ahead and replace our load right there. Do y'all see this? Now here's a tip. You see what this really is? That's just a source transform of a Thevenin circuit. That's all it is. Y'all see that? Give me a show of hands here. How many see if you do a source transform of a series resistor, series voltage, you get a parallel current, parallel. That's exactly what that is. But sometimes it's easier to do that. I am out of time. I'll do it one next time. We got a quiz next time. Now listen, next time I'm moving into chapter 3. So if you're smart, go read about capacitors and inductors. We're going to do transient circuits. There's really differential equations that govern, but I'm going to show you tricks so you don't have to solve differential equations. And I'm not going to use the cross